Now let us have some examples of two functions of two random variables. The first example, we consider a Cartesian to polar transformation. We have seen this example, so this is to reinforce what we know. So suppose that the random pair is defined by these expressions. So Z be equal to square root of x2 plus y2, which is the distance of the random pair to the origin. Sometimes we call these the envelope signal, or the distance with the origin, and the W to be this angle, so this arctan y and x. So this, if you want to use in MATLAB, you give this function, it calculates you an angle which is, so this is positive, and this is going to be between minus pi and plus pi. So it should be closed from this side and is open from this side. So the first thing is to determine d, z, and w, and this was all this set of pair of points x and y inside R2 in the 2D plane xy, such that g of x and y is smaller than or equal z, and h of x and y is smaller than w. Okay, so what I need to do is to determine these two regions, and then once I find these two regions, find their intersection, because here I have a common, which is the intersection of those points. Okay, so to do that, first I need to find, this is the first equation, and this is the second one. So the first one is that all those points that satisfy square root of x2 plus y2 is smaller than or equal z. So if z is negative, this set is going to be empty, and consequently dzw, this one is going to be empty. So for z negative, you are going to have this dz and w is going to be an empty set. Or if this guy w is not inside this interval, you have or if w is smaller than or equal minus pi, then you get this one. And consequently from here, f z and w of z and w is going to become 0 for those values. So for these values, the Jones CDF is 0. However, if z is bigger than 0 and w is bigger than minus pi, smaller than pi, then I could determine this. What is the set of xy points in the 2D plane which are smaller than these? So obviously, if I draw x2 plus y2 equal to z, this is going to be equation of a circle. So the equality here, this equality means a circle with a radius of z. And because I have inequality, means that all the points inside the circle and on the circle. So this first guy says inside the circle of radius z, or on the circle. The second one says that all the points with an angle of less than or equal w. So from here, if I consider the equality, if I say arc tan of y and x equal w, this will become a line. This will become a line with an angle of w. So I draw a line with this angle of w, and this side, this is for equality. So all the points on this blue line satisfy this one. But if I say that this should be smaller than or equal W, that means that below this line and above this line. Okay, so so this the second set here, this is gonna be this blue area. So this line and anything here. Now I have to have the intersection of all the points inside the circle and all the points which are blue. Okay, so the intersection is going to be where? So the intersection is going to be the points which are in here, inside this arc. So the radius of the arc is Z, and this angle of arc is W. So obviously what I could say is that f z w of z and w is going to be double integral of the joint PDF of x of y, fx y of x and y, dx dy, and the boundary here, the boundary of this integral should be such that it will cover integral over that. So basically we have to do integral of this function over this light red one. So this boundary you have to write the upper bound and lower bound of these areas such that you could integrate over this arc. So we can summarize. So you can do this integration in x and y domain, okay? Or you could convert this one and do the integration in the polar domain. Obviously, you know that dx dy is always equal to r d theta. So you can do integration over polar. So in polar domain, the range of r varies from 0 to z, and theta varies from 0 to w. Because what we know is that theta should be between 0 and w, and r should be between 0 and z. So this determines the same arc. I was able to do the integration over x and y because I have this one, okay? So in this area, so this is my x, and here this is z, and this is a radius of that. So so what could I say is that depending on the values of w, because if w is smaller than pi over 2, I could say that x for a given y, okay, so y, so if I write integral here for the range of y, so the maximum value of y, the minimum value of y is 0 for this value. If I have this one, I could say that f z and w of z and w is going to be y is going to be between, because y is positive and is smaller than this one, and obviously you can calculate because this is w, this is the angle, so here is going to be sine of w of w and then times z. So the maximum value of y is z sine of w. But then for a given value of y, x varies from this line up to this one. So x, so this is variation of y, and the variation of x varies from this line. So this is an equation of a line. So you have tangent of w times x is equal y. So is the lowest value, which is tangent of w times x, and the maximum value is this guy, because on this circle you have x2 plus y2 is equal to z2. So from here, the value of x can be calculated as a square root of z2 minus y2. And then you will have to write fx y of x and y. And then you have to calculate integration with respect to x. And once this integral is done, you integrate it with respect to y. But obviously, the integration in polar domain is much easier because here you have a rectangle, here you have a complicated curve. Now, if in this case, if you have the pair of x and y, they have a normal distribution, which is given by e to the power of minus x2 plus y2 divided by 2 sigma 2 divided by 2 pi sigma 2. If you substitute this one in your function, you can easily simplify this. Now, if you do the integration, you get a distribution like that. So this distribution is decomposed. This is only a function of z. This is a function of w. So you could say that this is f z of z and this is f w of w. Therefore, they are independent. This is a uniform distribution and this is a Rayleigh distribution. So what we conclude is that in this example, if you have a jointly normal distribution with the same variance, zero mean, and they are independent, in that case, the radius and angle, they are also independent. The radius or the envelope has a Rayleigh distribution with this one, and the angle has a uniform distribution between 0 to 2 pi or minus pi to pi, depending on how you define the angle. They are also independent. So here we had a couple of examples of two functions of two random variables.